not unlike Hurricane Rita, from Hurricane Ike, we learned that most of the damage to the grid was not caused directly by winds or water, but rather by toppled tree limbs and trees that knocked out wood distribution poles and other transmission distribution infrastructural elements. Observation number 2 is that diesel backup generators are not reliable. And so I should differentiate backup generators from CHP systems. Diesel backup generator is simply in place to provide a short amount of power for 24 to 48 hours, whereas an installed CHP system is designed to provide power depending on the needs of the system at a continuous rate. And later on in the session, Krishnan will go into further detail. But for now, we can make these observations about the performance of diesel backup generators in the wake of some of these natural disasters and in the last few years. Number 1 is that some backup generators simply don't start when they're called upon. Second of all, most backup generators start but can't maintain power throughout the length of the outage, which, as we've learned in recent years, that outage can last up to several weeks. And these backup generators simply can't maintain power that long, either because they fail or because they run out of fuel. Thirdly, much of the damage is related to the loss of HVAC, that's heating, ventilation, and air conditioning. So in other words, humidity infiltration can result in extensive damage to floors, ceiling tiles, medical supplies, and equipment. So there's collateral damage, so to speak, associated with losing power. And lastly, most backup generators often don't or can't power chillers. And just to elaborate on this observation, most of these quotes here are from are in reference to the widespread northeastern blackouts in 2003 that resulted in I want to say 8 states and parts of Canada that lost power. And as you can read here, half of the New York's 58 hospitals suffered backup failures during the blackouts. The next one, as you can read, generator failures at a Verizon office caused communications gaps for 911 dispatchers. And then next, a lack of backup power allowed 145 million gallons of raw sewage to be released from a Manhattan pumping station. And then lastly, just to summarize, a number of prisoners were trapped inside a prison and almost drowned to death, again because of this collateral damage associated with power outages. Observation number 3 is that those with power during and after the storms are capable of self-generating electricity with natural gas. Case in point, the Mississippi Baptist Medical Center, located in Jackson, Mississippi, was able to sustain power during and after Hurricane Katrina. Why? Because it has, and still has, an installed CHP system. So even though the grid was down for 52 hours during Hurricane Katrina, this medical center, which is a full-service hospital, was able to maintain nearly 100% operations throughout the course of the outage. And to draw parallel examples to the northeastern blackouts, here we have several facilities that were able to remain operational even when the grid went down. Why? Because they had on-site CHP systems. Observation number 4 is that natural gas was widely available throughout the region on high-pressure pipes. Natural gas is the most prevalent fuel source for CHP systems, and because they're underground, they're able to weather the storm, so to speak. Tulane University, for instance, has a CHP system, and despite flooding, despite the grid getting knocked out, the CHP system was able to remain operational. And I've already mentioned the Mississippi Baptist Hospital. Last observation we can make is that critical infrastructure operators may be held liable in the future for failure to secure energy. As we speak, there are a series of civil trials underway that will determine whether or not Pendleton Memorial Methodist Hospital should be held liable for failing to take adequate measures to secure their power source in the event of a blackout or the grid outage, as occurred during Hurricane Katrina, when a number of patients whose life support systems or ventilation systems were unable to be powered any longer, and these patients died. So the families of these patients are currently, or several of these families are taking Pendleton Hospital to court to determine the extent of their liability. And even though there are damage caps in cases of medical malpractice, what's interesting is that these cases are seeking damages under general negligence, which are not capped. So time will tell what the outcome of these cases will be and what the impact will be on other state courts, which can certainly be informed by the outcomes of these decisions for similar cases in their states. I will now turn the floor over to Krishnan, who will explain what CHP is all about.
Thanks, Ross. This is Krishnan Umamaheshwar, and I work along with Ross in the Department of Energy's Clean Energy Application Center. I'm primarily responsible for project support, and I'm going to be addressing two questions. The first question is, what is CHP as it pertains to the bill? And the second question is, what a feasibility study is and how we go about doing a feasibility study. Now, as per the bill HB 1831, CHP is defined as generation which is located on site at the facility. It should be the primary source for both electricity and thermal energy for the facility. It should provide all of the electricity needs to power the facility's critical emergency operations for at least 14 days. It should have an overall efficiency of energy that exceeds 60%. Now, very fundamentally, this is how your CHP system actually looks like. The most common fuel used in CHP system is natural gas, and as Ross explained before, natural gas is particularly handy at the time of hurricanes because your natural gas pipelines are underground and they are much more relatively immune to natural disasters when you compare them to wood poles or transmission lines. Now, the CHP system could be any number of configurations, and it could be your reciprocating engines, it could be the gas turbines, micro turbines. So that generates both electricity and heat. Now, how do you capture the waste heat? You can use the waste heat for either domestic hot water to provide the space heat for the building, or through driving the steam through a steam-driven chiller